Arturo?
Hello? Hello, hello, hello. Can you hear me?
Arturo?
Yes, I'm here. Can you hear me? Can you hear me,
Can you
Hamid?
hear me?
Yes, I can hear you.
Arturo, do you hear me?
Yes.
With
Hello? Can you hear me?
I hear you. I hear you.
Okay,
There was
fine.
something wrong. There was something wrong with the servers of webinar, and I really apologize everybody to make interruptions. The live video also on YouTube has ended. I started another live video. Sorry for this interruption, and there's nothing we can do, and it's just the webinar servers. So you can continue the live event if you want. It's okay for me.
Yeah, okay. Let me know if something bad will happen. I'm okay.
Okay, I'll text you. Just keep closing on WhatsApp and we'll be fine. Okay?
Okay, cool. Okay, let's come back
So
to
I'm
the...
leaving as well.
Okay.
If I close the camera, are you able to represent as well? Close just camera and mic.
Sorry, if I cannot hear you.
If I close the camera and microphone, are you able to continue the webinar?
Yeah, I'm able. Yeah, I'm able to do it.
Okay,
yes.
okay. I'm closing it, but I'm here.
Okay, perfect. Okay, so here we go again. I hope that now it works. Thank you so much for the messages I'm receiving now on WhatsApp, Instagram, and Facebook. Thank you so much. I'm sorry for the technical problem. So I come back to the previous step in order to because probably you missed some steps. So let's come back here. Okay, so we were saying that I created my 4 points on the rectangle, my 4 points on the as discontinuity points here. I merged them together, and now I want to split my rectangle using those 8 points. So we are going to use once again shutter, same procedure here.
Arturo.
Yeah.
We can't see your screen. It's just 80 on the screen.
Okay.
I think you need to share your screen.
Okay, I'm doing it again.
Yes, now it works now. Perfect.
Okay. So does it work now? Can you see the screen?
We see it. Thank you. Appreciate it.
Okay, cool.
Great. Thank you.
Okay, so I was saying once the 8 points on the rectangle are collected inside the merge component here, we can split the rectangle using those points, but it's not possible to directly use this set that you can see here and connecting them here like this, because shutter needs the t parameters of those points. In other words, if you have a curve like this and you have a point here, for example, we have the x, y, and z coordinates of course, so refer to the X, Y, and Z axis, but we also have the t parameter of this point, which more or less will be 0.5. Once again, t parameter ranges between 0 and 1. So we need the t parameters in order to actually split our curve. So every time you have to do this kind of conversion from XYZ to t, we have this component which is called curve CP, curve closest point. So we want to convert those points. So in other words, we can write something like this. So from XYZ to T. So our points are coming from the merge component. And of course, we need to set the reference curve from the conversion. So like this. So now we can actually split our original rectangle using the 8 points. So as you can see here, we are collecting 8 points, 8 because we start from 0, arc-like curve from here, and 8 linear segments from the second shutter component. Now, my idea is to create a set of surfaces by lofting the arc from the original circle with the external segments. So we want to create something like that. Okay? In order to show you also in Rhino, the idea is to create a kind of surface between each curve and each segment like that. Okay, so the first thing to do is like merging them together. So this one goes here and this one goes here. Okay, but if you check the panel, which gives us a kind of overview of what's happening inside the component, now we have the whole set of segments inside a single list. Actually, we want to create a list divided into couples in order to have, in a way, one arc and one segment, one arc and one segment, like this, a kind of one-to-one relationship. Now, in order to do that, with a panel here, you can, for example, you can graft this one. So right-click and graft. So as you can see, we are actually creating this kind of couples. So we have like several rooms. Inside each room, we have one arc and one line. So we can also, now we can loft them with the loft component. Okay, and it works perfectly. But as you can see here, we are not actually creating a loft between, let's say, this one and this one, but it's clear that our set of items, set of objects, they are like shifted. So there is a component which is called shift list. Okay, so we can, for example, we can shift this list here about 1 unit. Okay, now when you apply the shift list, as you can see here, we are losing this kind of one-to-one correspondence because this is a data tree problem, something that we cannot cover in this webinar, but probably you are already familiar with this topic. We are adding a new kind of generation in our system. And so we cannot properly match data. So in order to fix the problem, let's say you should go once again here. You can click on Simplify, D2, and you click on Simplify again. So as you can see, we have now once again the couples, and we perform the right loft between the corresponding set of curves, as you can see here. Okay, so let me turn off the preview of everything here and everything here. And so this is, let's say, we can move on from this section. Now, we have 8 surfaces. They are untrimmed surfaces, as you can see if I connect a panel here. Okay. The second step is like we want to convert the 8 surfaces into 8 meshes. You know the difference between a NURBS geometry. So a difference between a surface and a mesh is like NURBS is a mathematical object, while a mesh is just a collection of points. We can use the mesh surface component, allowing us to create a grid on top of it, as you can see. If you don't see actually the mesh edges, it depends on a display option, which is called preview mesh edges. You can also click on Ctrl+M in order to activate and in order to enable and disable it. And of course, we can also set the, let's say, number of subdivision in U and V direction. So let's use, for example, 22 for U and V. Okay. We are not just creating a single mesh, but they are actually, many of them, they are 8, once again, as you can see here. So my suggestion is to use the join meshes and weld, which is a component available within Weaverbird. Okay, this one here. We need to flatten the M+ input in order to have the whole set of geometries of meshes inside the same room. And we need to toggle the W input to true. Something like that. Now, as you can see here, we have now just one single mesh. I mean, the geometry that you can see now on the screen is just one individual mesh. Everything is like blended together. And of course, we can also extract the vertices and edges from this mesh. As you can see, and as you probably already know, a mesh is like made by a set of points connected by straight lines. So using 2 components from Weaverbird, so vertices component and mesh edges, you can extract both. So vertices and edges are selected using those tools. Okay. Now, the next step, if you take a look to the British Museum, like the roof geometry, basically it can be created with a mesh relaxation process. In other words, we can start with a flat geometry, and we can also it is possible to apply a set of forces in order to get through a physics engine the final shape. So in this case, we are going to use Kangaroo engine, Kangaroo 2, which is already embedded inside Grasshopper. And in order to properly set the list of operations to do, it's important to apply a set of forces. The first thing to do is like converting our edges into a set of springs. In other words, we have a set of edges here. They must be converted into, let's say, springs in order to simulate a kind of elastic behavior. In Kangaroo 2, you can go in side the goals line subtab, and you can find this one which is called length line. So the first thing to do is like putting length line here, and we can connect this one here. Finally, we need to like measure the edges length using a component which is called length, by the way, this one. And I suggest to perform a multiplication between values coming from this. Be careful because this one is like length is not list length. They are different components. It's important to see that we have a C input here. So I'm going to do a multiplication between this one and a value between 0 and 1. But let's put it to 1. We can set this one like this and then like this. Okay, so this is the start point from the spring generation. In other words, we are now converting our lines into a set of elastic springs like this. We are going to play with this value later on. Okay. Now you can see this like system as a flat membrane with a set of points. We are going to apply a set of loads upwards, so according to the z direction on each of those points. The load component in Kangaroo 2 is available in Kangaroo, goals point, and we have load. We have to apply loads in our vertices here, and direction, unit z. We should connect this one into the FV input, which means force vector. And let's use just an ideal value here, which is about 1. It means that we are applying 1 to each particle here in our system. And a super important step now, we also have to define the anchor points of our system. In other words, if we want to apply this kind of elastic deformation, it's important to set anchor points around the rectangular frame, but also around the circular frame here. Okay, in order to do that, there is a component in Kangaroo which is called naked vertices. It should be connected directly to our mesh. So from mesh join here, we can go like this. And as you can see, we have several outputs. You can use a point component here like this, naked points, and I'm going to turn off the preview of this one. So as you can see, we are selecting just the so-called naked points because we want to anchor our membrane around the rectangular frame and circular frame like this. Okay. So we have loads from here, springs, and we need to define the anchor points. So let's go in goals point here. We can find, we are still in Kangaroo 2, anchor, and this one goes here. Okay. In Kangaroo 2, they are called, we can call this one is the anchors. They are called goals. They are the goals of our system. We have to merge them together. And this one goes here. Now, actually, we also want to show the mesh during the deformation during our simulation. So it's important to use also here this component, which is called show. And we want to show the original mesh. So let's connect this one here. And I suggest, so let me remove this merge again, sorry. And then I connect this one here, this one here, this one, and this one. So when you want to involve the original geometry within your simulation, I suggest to use, and I will show you why later on, it's important to use the show component in order to show it, and should be the first input of the merge component, and I will show you why. So this is the system. We have 1, 2, 3, 4 goals. We just need the simulation engine. So Kangaroo 2, main. Here we have the so-called bouncy solver. We have many solvers here. I'm going to use the bouncy solver that gives you actually the idea of like live simulation with an elastic behavior of our geometry. So let me put this one here. I use 22 subdivision just for simplifying the job. Let me use just 10, but later on we are going to change this value. Okay. We need to flatten the goal object input. And then we need 2 toggles. You can use also a button if you prefer, but it's better to do. So if you put a false toggle to on, you are basically turning off the engine. We can do the same thing here for the set, but it's the opposite here. If I set this one to false, it means that is basically working. Now this one goes here. Okay. As you can see, we can read here post. Let me change this one a bit. When you apply the bouncy solver, you can see the particles because they are part of our simulation. I can also turn off the preview everything. Okay. If you take a look here in the output, we have several outputs. Basically, the simulation of the old mesh, which is the first object since we put show on D1. So that's why you can see the mesh, and that's the reason why it's important to connect show on D1. And then we have a set of line. Since we want to simulate only only the first object, you can use, for example, list item in order to analyze only this one. Or in alternative, you can use a mesh component like this. And you are selecting only the mesh. Of course, in this case, we are also creating a list with a set of null objects. It's up to you if you want to use list item this one. If you use, for example, a mesh component which turns red because we have null objects, you can also go on. It's not a problem. I mean, it doesn't affect the next part of the algorithm. But anyway, let me turn this one off. As you can see, we are displaying the correct mesh. And I can double click on this guy here and this guy here. Okay. So true on, it means that the simulation is running. Reset should be on false. You can see running here. And we got a deformation of our membrane. So let me do again. Like this. And like this. Okay, the simulation is good. We are getting closer to the final geometry, but as you can see, we have a kind of edgy behavior on the corner. Also, if you go in a top view, as you can see, we don't have an actual continuity of our edges here, but you can see that we have a boundary, we have a discontinuity edge here, 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 and here in the four corners. And also, the final mesh is not really tense and clean, but actually we get this kind of bad behavior here and here. So in order to fix this problem, it's very simple. We can go back here. If you remember, I told you that we have our edges. This multiplication component allows you to set if after the simulation, the edge should get the same length, or if you want to reduce it, for example. As you can see here, we are changing this value. And now the final output is way cleaner, let's say. You can also change for example, the force. You can change this value again. And now, as you can see, the final mesh now is absolutely cleaner and more tensed. So the length input is like crucial in order to, and you should play with it in order to get relaxed mesh. As you can see, if I change once again this value to 1, we are getting an object with edgy corners. Okay, now let's change something like, let's put this one to 1 again. Let me increase the number of subdivisions. 1. As you can see, we are getting a kind of monster, because in general, you don't have to change like important values in your algorithm. Meanwhile, the simulation is running. So it's better to turn off everything and turn it on again. So now this is a mesh with a higher number of cells and edges, of course, more defined, let's say. If you want to pause the simulation, so if you want to see the final configuration, but you want to stop the solver, you want to pause the solver, you have to double click here. So as you can see, we have pause. So also the navigation gets smoother. Let me turn the building on, for example. You can see the output now. We can go also basically inside. Oops. Okay. Now this is the first output that we are getting. So is the pure output from Kangaroo. But as you can see, we have two main differences with the original roof. First of all, if I come back to the pictures and images, as you can see, we don't have like a square grid on top. From Kangaroo, we are generating a rectangular grid, as you can see, because we simulated the deformation of a square, of a quad mesh, as it is defined actually. In the real building, we have, on the opposite, we have a triangular mesh for a simple reason, because if you have triangular faces, the glass panels, they are by definition, by geometry, they are flat surfaces. So in terms of manufacturing and cost, of course, they are cheaper and like easier to be assembled together, manufactured and assembled together. So this grid is a triangular one. So in order to get something which is more realistic, we need to switch from a rectangular grid to diamond one. So this operation is not super easy, as you can imagine, but actually we need to rely on a plugin which is called Paneling Tools. Is a very powerful plugin in order to create, let's say, complex grid and something like that. So I will give you, if you didn't install Paneling Tools before, we can do just 2-3 minutes of break in order to give you time. If you just want to if you want to download it, you can download it from Food for Rhino. It's a super easy installation. It's a file that can be installed just by double clicking it, and it will install paneling tools on Rhino, both on Rhino and Grasshopper, because it's also a set of Rhino commands. So just 2 minutes, and I will start with the second phase. Will be let's say a little bit more complex, but nothing like scary or too much complicated. And we are going to use paneling tools in order to switch a square grid into a triangular one. So let's talk in a while. Okay, here we go again. Can you please, Hamid, give me a feedback that everything works?
Everything works, and I hear you.
Okay, can you see the screen?
I see the screen.
Okay, amazing.
Thank you.
Okay, so I was mentioning that now we are going to use paneling tool in order to convert a square grid into a triangular one. First thing to do, starting from our mesh. Once again, it's not a problem if you can see that this one is in red. Okay, the first thing to do is we can use the warp weft component. Okay, warp weft allows you to extract if you have a mesh with, of course, U and V direction. You can extract only let's say, the curves in one or in the other direction. So warp weft component, this one goes here. Okay. Also, this one will turn red, but don't be afraid of that. And let me check here. Once again, it's super important, guys, to have the curve edge visualization. So Control plus M if you cannot see the edges. And if you can see here, I can connect this one like this. And I'm turning off the preview of warp weft and also of our original mesh. I'm going to turn off the building. So as you can see from the A output, I'm getting only the U direction, let's say, and from B, the B direction. Okay. So the A are parallel, let's say, to the circle, as you can see. And actually, something that usually happens when you do something like this is like our curves, they are not organized, let's say, from the center toward the boundary, but they are like randomly distributed. We can check it in many ways. For example, we can use the point on curve component and no, actually not exactly like that. Anyway, I will show you later something. In general, they are not organized they are not organized from the center toward the outside, but they are randomly distributed inside the list. So the first thing to do is like we need to organize them from the center toward the outside. How? We need to join them together because we don't have individual curves, but we have many segments. So the first thing to do is like join them together. So join curves. Okay. Now, as you can see here, and we have a set of polyline curves. Okay. If you use, for example, now point on curve, and a point list component, for example, like this. Okay. If you see the list here, we have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And then we have 11, 14, 13, 12, 15, 16. So basically, when we are going toward the circle, they are not like evenly, I mean, they are not organized within our list. So the first thing to do is like we need to organize them together in a proper list. So we can do something like that. I'm removing this one. And first thing to do, we need to find the center of this circle here. Maybe one way is to calculate the area here. So the area component connected with the original circle is giving us the center. Okay, so the first thing to do is this one. Okay, and we need to organize our set of curves according to the distance between each curve and the circle center. So in order to do that, there is a component which is called sort list. You are probably familiar with it. Like this. And we want to sort our curves. The object to be sorted, they go here in A. And inside the key, we need to define the logic for organizing our objects. So we can measure, we can calculate the distance between the center of each curve. So we can use, once again, point on curve. That goes here, and center here. Let me turn off the preview of everything here. So, and this one, like this. Okay, now we organize our curves from the center toward the external boundary. Okay. And this kind of organization of sorting should be done also on the other set of curves here. So let me turn off the preview of this. Now, we need to find a different logic now, because they should be sorted around this curve here, which is our circle. And we can do something similar. Once again, point on curve, which gives us the center, of each curve, like this. But before, we need to join, as we did before. So join curves, and then this one. So let me organize the algorithm. So, okay, so we have join here, join here. And in order to sort around this curve here, there is a component which is actually called sort along curve. Our curve is once again the original one, which is the circle. So we can connect the original curve. Like this. Okay, so we have the first, let me turn off the preview of this one. So now we have the first list from this one and the second list from this one. But actually, now this is organizing, this is sorting only the midpoint for our curves. So we can use list item. As you can see here, the sort along curve is giving us the indices for the sorted points. So we can use the same indices in order to select our curves. So doing like this and like that. Okay, now we are actually selecting our curves, organizing them around the central circle. Okay. So this way we have our curves like organized in a proper way. Now we need to start using the paneling tools component. The first thing to do is like intersecting the two sets of curves in order to extract the intersection points. So let me go in, we need to use intersect curves, this one here. Okay, so we can connect this one here and this one here. Okay. Of course, we already have those points before, but they were not organized in a proper way. So those like steps are super important in order to have a proper set of points organized in the proper way. And so now we can extract them using the intersect curves component. this is a component coming from the paneling tool system. So paneling tool, grid, and then you can find in intersect curve. Now, there is an operation that is not easy to like simplify right now, but we need to use a component which is called wrap grids. So we can use this one. We need to connect this one here, and we just have to set 1 for D, which is actually is the direction according to we want to organize the grid itself. So this one can be set to D. And we don't also need to find the starting index, to set the starting index, which is 0. And this one goes here, like that. I know it will look like an obscure passage, but it's something that we need to do in order to really convert this grid into a diamond one. Now, the conversion is super simple. If you go in grid utility, you can find here convert to diamond. So we can do something like that. And this one is connected here. Okay, nothing happens actually. But if you going to use a component which is called generate borders is another component that you can find in paneling tools and panel 2D subcategory. If I connect this one here, let's give him a second. We need to set PS, which is the shape of our border. We need to set this one to 0. Okay. And as you can see, we have the diamond grid. So basically, if you don't use the wrap grids, I want to show you what is going to happen. You don't get, let's say, a closed diamond. That's why you need to apply this component with those settings. Putting this one to 0, basically, you get a kind of periodic, let's say, grid. So this is what this one is like mandatory if you want to create, like let's say, a diamond grid, which is closed and you don't have any kind of, let's say, gap. Now, if you activate, for example, we come back to the, to the Kangaroo part, and I connect the A here. Okay, as you can see, we switch from a square. From Kangaroo, we got the code-based membrane, which was far from the actual, let's say, building. And now we have something which is absolutely consistent with the real geometry, as you can see here, but also here. Okay. So basically, we have one diamond with an edge inside. The reason why we have this kind of actually the picture is was taken by, okay, more or less is like this. Now, if you want to, the reason why we also have this kind of second layer, it's because if you have 4 edges, as you probably already know, is absolutely not guaranteed that your surface is flat. If you have 4 points, you don't have just one flat. You know, the planarity of your surface is not guaranteed. Only if you have 3 points, the planarity of your face is guaranteed. So basically, they cut the geometry in order to have the single, let's say, the single quad, the single diamond, in order to have 1 and 2 geometries that they are actually flat. Okay, now we can just do something about this procedure, which is actually, in order to complete it, it takes some time, but I can show you something in a very easy way. So just for summarizing the steps after the Kangaroo, with warp weft, we selected the curves into 2 different directions, U and V. We joined them together and we organized them in order according to the distance from the center, in this case, and along the circle in the second case. And then we applied 2 paneling tools components, actually 3 components: the intersection of curves in U and V direction, wrap grids, which is useful for the conversion, and finally we converted the original grid into a diamond one. Finally, we generated the borders, because here we are just like generating a set of points. From this set of points, we can create a set of borders. Okay. Now, if you want to create a set of flat surfaces on top of it, there are many ways. For example, we can explode this one. Okay, so if you focus on the single diamond, now we have 1, 2, 3, 4 segments coming from this one. And then we can basically, let's say that we have 0, 1, 2, and 3. We can create a loft between 0 and 3 and 1 and 2 in order to get 2 single flat surfaces. So let's use list item component from this one. Then I'm extracting 4 output. So once again, because we have like 0, 1, 2, and 3. I don't know actually if this one is actually the order that we have in the list item. But anyway, we can, let's say, we can merge together. We can just try it. For example, 0, which is this one. And let me try with 2 consecutive values. We can do like this. And then loft. Okay. As you can see here, we are creating a loft between this curve and this one, but actually we have a kind of flipping, because curves in Rhino and Grasshopper, they have a direction. So we have this direction here and this direction here. So we are creating a kind of loft between this one and this one. And so we have a kind of twist. Super simple to solve, to fix. We have a flip component, this one. Sorry, not this one. This is for surfaces, so we have to use flip curve, sorry. So flip curve component. This one. Perfect. As you can see here, we have okay. Let's do the same we can do copy and paste. Now we can do it for set of curve 2 and set of curve 3. Okay. Okay, now this kind of approach, of course, since we are like lofting, we are getting a kind of empty set of diamonds here, where we have the seam and also around the boundaries. Something that it's very easy to fix. If you want to do it also with a super simple script, can be done in a very easy way. But we did basically the 90% of our job. Now I can also turn off the preview. That's interesting because we actually get set of flat surfaces. So let me preview, turn off the preview of everything. I want to bake also those two geometries. Okay, bake. Okay, I'm baking them. Now they are, I can also turn on the building itself. Okay. Now it's very important because now they are flat. So you can basically like manufacture and them in an easy way. Since they are flat, they are not double curve geometries. And we can also, starting from the borders, for example, if you use component like, let's say, mesh pipe, with 0.6 for radius, more or less. Let me try to do it. Okay, it should be way less. Okay. We are also giving a kind of three-dimensional aspect to our pipes. Okay, let's bake them together. So now it's not only interested that we like simulated, let's say, the final geometry, but it's interesting that we just started from two curves, one rectangle, one circle, and we created a super complex grid shell with a diamond structure and with a set of flat like panels. Of course, you can complete once again the missing parts, which is super simple, but that's very interesting. The idea of creating, replicating a complex, let's say, architecture, just starting from two curves, and like also exploring some optimization step, parallel to Atlas in this case. Okay, that's it for our tutorial. Hamid, I don't know if you can hear me.
Hear you, Arturo.
Okay.
But I can't hear you.
Okay, thank you so much for the attention, guys. I hope you enjoyed the tutorial. Let me know if you have some comments also through Parametric Architecture page.
Thank you, Arturo. Thank you so much for such a great webinar.
Okay, can you hear me?
Thank you.
I'm here.
Goodbye, guys.